To proceed, we begin by abstracting the underlying problem. So imagine we have a large population, and we abstract it by drawing, let's say, a box or an urn, and the elements of the population, people, creatures, widgets, we abstract away as balls of one of two colors. So now we have a dichotomous population, in this case, an urn with orange balls and blue balls. The fundamental question is the following. What fraction, say p, of the balls in this urn are orange? The moment I understand this, I understand how the subpopulations are distributed in the underlying population. Now, how would one go about estimating this? Well, naturally enough, one way to do this is to simply make an exhaustive count of every single ball inside the population. Count everybody in the general population and examine who is of type orange and who is of type blue. If one did this for the figure at hand, you would find there are 360 balls in total, of which 101 are orange. But of course, this gets rapidly wearing. And in a large population, this becomes unworkable on a routine basis. Right? For instance, in a political setting, looking at the persuasions of every individual in the country is essentially what we call a general election. But of course, one can't run a general election every year, or even every other year. So, in such settings, we still wish to understand how the subpopulations are split up. In politics, this becomes important to understand what kinds of legislation should be passed which is representative for the population. In the environment, it becomes important to understand the extent to which you have an invasive species spreading into a native domain, and so on. It is natural now, if we can't count everybody in the population, to query what happens if we sample randomly from the population. So let's consider what happens if we take a random selection X from the population I've given you. Now, the element could be an orange ball. Now, what are the chances one draws an orange ball if one selects at random from the whole population? Well, there are 360 balls, as I've informed you, of which 101 are orange, and therefore the chance, the probability of selecting an orange ball is 101 over 360, and so p is approximately 0.28. The chance of selecting a blue ball, likewise, is 259 out of 360, and that's about 0.72. Now, what is key here is this. The proportion p is fixed, it's 0.28, but it is a priori unknown to us. And what we would like to do is, what we would dearly love to do, is to be able to estimate p accurately without having recourse to counting everybody in the population. Naturally, from here, we think about sampling repeatedly and independently from the population. Let's abstract out the whole picture now. You see, there's an underlying population with elements of two flavors, orange and blue to begin with. Well, we could think of this abstractly as some collection of objects, a proportion p of which is orange, and a proportion q, 1 minus p of which is blue. Now, names orange and blue here, Republican, Democrat, Python, alligator, are just names. As far as the estimation problem is concerned, they are irrelevant. We might as well simplify our notation and the way we compute it by calling the elements of one type the number 1, the elements of the other type the number 0. Now, what does a random sample look like? Well, a random sample could be either of type 1 or it could be of type 0. In other words, picking a random element is equivalent to the toss of a metaphorical coin. Now, what's different here is we're tossing a coin. It has got a certain bias towards success, P, but we do not a priori know what P is. Our estimation problem is, given the coin, to determine what P is. Now, there's some nomenclature which goes with this, and there's some history which goes with this, and we should take stock of this. The first thorough examination of sequences of coin tosses was undertaken by Jacob Bernoulli, the patriarch of the Bernoulli clan, perhaps the most famous clan in mathematics, and his work was published posthumously 7 years after he died in 1713. And the work was called the Ars Conjectandi, the art of conjecture. And in it, Bernoulli fleshes out the mysteries of coin tossing to a hitherto unimagined level. And so, from that point on, we have called coin tosses Bernoulli trials. And so, here is another name, or a sequence of names, for the underlying experiment. Selecting an individual at random from the population, when the population is dichotomous, corresponds to flipping a metaphorical coin with a fixed but unknown success probability, P. We will call such a coin flip a Bernoulli trial with success probability, P. We will denote it, the outcome of this trial, by a letter X. X is a chance variable. It's going to take one of two values, 1 or 0, orange or blue, with probabilities P and 1 minus P respectively, and from now on in this context we will always write 1 minus P to be Q. Here now is a setting. Sampling from an underlying population is equivalent to the toss of a coin. Now, how do we go about determining what the bias might have to be? Well, naturally enough, we sample repeatedly. Okay, and so let's move on and consider a setting where instead of a single sample, we sample repeatedly from the population. Of course, the sampling is with replacement and is independent and is bias-free. What bias-free connotes in this context is that, in principle, I can pick anyone in the population, all elements being equally likely. This, of course, makes sure that I'm not selecting from one segment of the population or some other narrow region of the population. We select from the whole population because I want to say something about the population as a whole. Naturally enough, I'd like the sampling to be with replacement because otherwise I'm denuding the population and the underlying proportions will change from step to step. To avoid this, we make sure sampling is with replacement. And, of course, we want the sampling to be independent. So we now have the context that we are very familiar with, that of repeated independent trials, and this is the simplest of those settings, the repeated toss of a coin. Now, if we toss a coin repeatedly, in this case I've shown you what happens if we toss it 12 times, then we get a sequence of outcomes, ones and zeros, successes and failures, oranges and blues. Here's a particular listing of a sequence of successes and failures, 0 representing a failure, 1 representing a success. Now, for this particular sequence, we've sampled from the population 12 times. We've got a particular sequence of elements in the population. Of this sequence, we are interested in asking how many are of type 1, how many are orange. And a simple count shows there are exactly 4 ones in that sequence. Out of how many? Well, out of 12. And therefore, the frequency of type 1 in the sequence I have drawn is 4 and 12, or 1 and 3. Now, you may recall that in the original population that had started with, of balls in the urn, there were 360 balls and 101 orange balls. And therefore, the proportion of orange balls is about 0.28. We now get 1/3 in this particular sample. Now, that's pretty close to 0.28. I wonder if this is a more general phenomenon. So our fundamental question is the following. Are the subpopulation proportions in the sample that we have selected representative of the subpopulation proportions in the entire population. Would this be the case? Now, on the face of it, this does not look very promising. Imagine, if you like, a large underlying population, say, of a country, divided into two groups. That's a very large population, maybe 100 million, 500 million, perhaps 1 billion people. A typical poll, if you look at a newspaper, will look at something like the order of 1,000 individuals, if we're lucky. Why should the proportions in 1,000 individuals have anything whatsoever to say about a population which is 1 million times larger, a population of a size 1 billion? This doesn't sound reasonable at all. But perhaps we should examine this a little bit further to see what we can glean from the structure. So let's immediately abstract away the underlying problem. I'm going to start with a dichotomous population, one of the many types I've shown you or that you could imagine. I'm going to abstract away the process of random selection from that population by the metaphorical toss of a coin. In other words, a Bernoulli trial with a coin whose bias, P towards success, is fixed, but sadly, unhappily, unknown. We're going to toss this coin repeatedly a finite number of times. How many times? Well, ineluctably, of course, n times. What else would we call it? We'd like to have some generic number of trials and then see what happens as the number of trials increases. So in other words, we now have a sequence of coin flips, Bernoulli trials x1 through xn, each of them taking values 1 and 0, biased towards 1 with probability p, biased towards 0 with probability q. Of course, the coin flips are independent. This constitutes the raw data of a poll. Out of this, we abstract first the number of elements in the poll, in the sample, of type 1. Let's give it a name. The number of elements of type 1 can be obtained by simply adding the x's from left to right. Of course, every time an x is a 0, it has no contribution to the sum, and when an x is 1, it gives you exactly 1 to the sum, and therefore the sum of x1 through xn will be exactly representative of the number of ones or the number of successes. We call this naturally the accumulated number of successes in a sequence of Bernoulli trials. Let's give it a name, S for sum, and use a subscript n to remind ourselves that we're summing over n trials. So S sub n represents the accumulated successes in n tosses of a biased coin. How does our basic question get reflected into this mathematical substructure? Well, very simply. The fraction of ones in the sample is Sn divided by n. In our example, we had n was 12, Sn was 4, and so the fraction was 4 divided by 12. And our basic question is Sn divided by n a good approximation to the fixed but unknown p?